Hey everyone, welcome back to the channel. Today we are diving into something that powers almost every data science and AI project, NumPy. If you've ever worked with Python and data, you've probably heard of it. But do you really know why it's so powerful? Let's find out. NumPy, short for numerical Python, is a super efficient library for handling numbers, arrays, and matrices. Think of it as Python's turbocharger for math. While normal Python lists can store data, NumPy arrays store it in a way that's faster, lighter, and made for computation. With NumPy, you can process millions of data points in seconds. Matrix multiplications, statistical operations, linear algebra, all optimized in C under the hood. It's the backbone for libraries like Pandas, TensorFlow, scikit-learn, and even PyTorch uses similar array structures. A NumPy array is a powerful data structure used in Python for handling large sets of numbers efficiently. Unlike regular Python lists, a NumPy array stores all its values in a continuous block of memory, and all elements have the same data type. Because of this, NumPy can process data much faster, perform mathematical operations easily, and handle multidimensional data like matrices. This makes NumPy perfect for data science, machine learning, and numerical computing. Okay, let's start with install. For installing NumPy, we can use pip install NumPy command. And for importing NumPy, use import NumPy as NP. First, we need to import the NumPy, then declare the one-dimensional array. It's auto-generating by cursor. Okay, let's change some of the values. And then we can print the array along with its data type. I'm also trying a two-dimensional array, and we will print that array and its type as well. Okay, let's run it. Printed both single and multi-dimensional array and printed the result. Now you can see the result is printed and showing the array and its data type in console. Now let's see how we can initialize NumPy array in one-dimensional, two-dimensional, and three-dimensional array. A one-dimensional array is just a simple list of numbers arranged in a single line. A two-dimensional array looks like a table with rows and columns, similar to a spreadsheet. A three-dimensional array extends this idea even further. You can think of it as multiple 2D tables stacked on top of each other, like pages in a book. These different dimensions help us store and organize data depending on how complex the structure is. In NumPy, even though we work with 2D and 3D arrays visually as tables or blocks, the computer actually stores everything in one continuous block of memory. For a 2D array, we normally think of rows and columns like a table. But inside the memory, NumPy arranges all the values one after another in a flat sequence. It also keeps a shape value like rows, columns, which tells NumPy how to interpret that flat data as a two-dimensional structure. For a 3D array, we think of it as multiple 2D tables stacked like layers. In memory, NumPy still stores everything as one long sequence of values, but this time it keeps a shape like depth, rows, columns. The depth tells how many 2D layers exist. With this shape information, NumPy knows where each layer starts and ends and how to rebuild the 3D structure when you access it. So even though we see 2D and 3D arrays visually as grids or blocks, behind the scenes they are just continuous numbers stored efficiently, with NumPy using the shape to convert that memory into multidimensional views. And NumPy we're not limited to just 1D, 2D, or 3D arrays. You can actually create arrays with any number of dimensions. These are called n-dimensional arrays or end arrays. The interesting part is no matter how many dimensions you create, NumPy always stores the data in one continuous block of memory. What changes is the shape, a tuple that tells NumPy how to interpret that flat memory as a multi-dimensional structure. Let's try some samples. First, we will try for NDing, which gives the dimension of array. Yeah, it's printed as 2 now. Let's see the shape of array. For that, we need to use shape method. Yes, it is printed the shape as 2 by 3. Let's check the size of array. Yes, it's given as 6. Now let's check the data type. It is printed as int. Now let's check the item size. Yes, it is printed as 8. It is taking 8 bytes in memory. Now we can check the data attribute. It's printed the memory address. Now it's going to print as a single dimensional array. The reshape function in NumPy allows us to change the shape of an array without changing its data. So if you have a 1D array with 12 elements, you can reshape it into a 1D array like 4i3 or even into a 3D structure as long as the total number of elements stays the same. It's basically a way to reorganize the same data into different dimensions, which is super useful when preparing data for machine learning or mathematical operations. Now let's discuss on flattening array. Flattening an array means converting a multi-dimensional array into a single one-dimensional array. So if you have a 2D array like a table or a 3D array like stacked layers, flattening will take all the elements and place them in one straight line. This is useful when you want to simplify complex data, feed it into machine learning models, or perform operations that require a single sequence of values. NumPy does this easily using functions like flatten or ravel. Let's see how we can flatten a three-dimensional array using flatten method. For this, we need to only use NumPy flatten method. It listed to one single flattened array. The transpose of an array simply means flipping its rows and columns. In a 2D array, rows become columns and columns become rows. It's like rotating the data along its diagonal. For higher dimensional arrays, transpose rearranges the axes, letting you change how the data is oriented without altering the actual values. It's super useful in mathematics, matrix operations, and machine learning workflows. Now let's see an example of transposing 2 by 3 matrix into 3 by 2. It's converted 3 by 2 matrix into 2 by 3 format. NumPy makes math operations super easy because it performs calculations element-wise. That means the operation is applied to each element in the array automatically. Adds corresponding elements of two arrays. It is umming up by each elements and giving the result. Subtracts method subtract one array from another element by element. Now we can print the result and it generated the subtracted value. Multiplication in NumPy happens element-wise. That means each element in one array is multiplied with the element in the same position in the other array. This is extremely fast because NumPy uses optimized low-level code. It's perfect for scaling data, doing mathematical transformations, or applying formulas across large datasets. Division also works element-wise. Each element in the first array gets divided by the corresponding element in the second array. NumPy automatically handles floating point results, making it easy to normalize values or convert raw data into ratios. Power operations are applied to every element individually. When you use the operator, NumPy raises each element to the given power, like squaring, cubing, or applying exponential transformations. This is very useful in scientific calculations, machine learning preprocessing, or anytime you need to apply the same mathematical function across an entire dataset. Overall, NumPy makes these operations simple, consistent, and extremely efficient even when working with huge arrays. NumPy isn't just for numbers. It also has a special set of string functions that help you work with text inside arrays. These are available through np.char, which treats every element in the array as a string and applies the operation element-wise. With these methods, you can easily do things like converting text to lowercase or uppercase, joining strings, splitting them, replacing characters, or checking if a string starts or ends with something. The best part is that NumPy handles all these operations very fast, even when you're working with thousands of strings at once. So NumPy's string methods are super useful when you're cleaning data, preparing text for machine learning, or transforming large batches of text efficiently. Uppercase converts every character in the string array to uppercase. Lowercase converts all characters to lowercase. Title capitalizes the first letter of every word in each string. Capitalize capitalizes only the first letter of the entire string and makes the rest lowercase. Centers the string within a given width by adding spaces or a custom fill character. On both sides, left justifies the string by padding spaces, or another character on the right justifies the string by padding spaces, or another character on the left. This method splits each string in the array into a list of words based on a separator like space, comma, etc. It's useful when you want to break text into smaller parts for processing. Removes leading and trailing characters from each string. By default, it removes spaces, but you can specify any character you want. Great for cleaning messy or padded text data. In NumPy, when you add two character arrays, the operation doesn't perform math. It performs string concatenation. That means NumPy takes the corresponding elements from each array and joins them together to form a new string. NumPy does this using the np.char add function, which safely handles different string lengths and performs the operation element-wise. So instead of number addition, adding character arrays in NumPy is basically a fast way to combine strings. It's append hello Python to one string and world programming into another string. Super important statistics terms you'll hear everywhere: mean, median, mode, and variance. Don't worry, I'll keep it super simple. The mean is simply the average of your numbers. You add up all the values and then divide by how many numbers there are. It gives you a general idea of the central value in the dataset, but it can be affected by very large or very small numbers. The median is the middle value once the numbers are sorted in order. If there are an even number of values, we take the average of the two middle ones. The median is great because it isn't affected by extreme values, so it shows the true center more accurately when the data has outliers. The mode is the value that occurs most frequently in the data set. This is helpful when you want to know which value appears the most, especially in categories, repeated measurements, or survey responses. The variance measures how spread out the numbers are. If the variance is small, it means most values are close to the mean. If it's large, the values are more scattered. Variance helps us understand how stable or inconsistent the data is. Together, mean, median, mode, and variance give you a complete picture of how your data behaves, where the center is, what's common, and how much the values fluctuate. These four basics are the foundation of understanding any dataset quickly and clearly. In NumPy, working with statistics becomes very simple because the library has ready-made functions for all the basic calculations. To find the mean or the average value, we just pass our array into np.mean. NumPy does all the work, adding every element and dividing by the total number of items, so you instantly get the central value of your data. For the median, NumPy provides np.median. This function automatically sorts the values internally and picks the middle one. If there are two middle values, it averages them. This gives you a clean, accurate center point of the dataset. When it comes to the mode, NumPy doesn't have a direct function, but we usually use SciPy's stats.mode to find the value that appears most often. NumPy can still help us count occurrences using np.unique if needed. Indexing in NumPy is the process of selecting specific elements from an array using their position. Every item in a NumPy array has an index starting from 0, and indexing gives us direct access to those positions. NumPy indexing is extremely powerful because it gives you precise control over which elements you want to access or modify. And the best part? Indexing usually returns a view, meaning it directly references the original data without copying it, making operations faster and more memory efficient. So indexing in NumPy is all about locating specific data points, whether it's a single value, a full row, a full column, or an entire block in the simplest and fastest way possible. Now let's see some examples. I declare three types of array: one-dimensional, two-dimensional, and three-dimensional. Let's print the fourth element of one-dimensional array using index. So it will array of 3 and the result is 4. Now we can print the second row, second last element of two-dimensional array, and it will print 5. Yes, it is printed second row first index value result 5.
When we write R3011, we are accessing a single element inside a three-dimensional NumPy array. A 3D array is arranged like layers, rows, and columns. So the first index selects the layer, the second index selects the row, and the third index selects the column. That means R3011 is telling NumPy, go to the first layer, then pick the second row, and from that row, take the second column. This is how we navigate through the depth, height, and width of a 3D array to extract exactly the value we want.
The result will give 5 from 0 index. First row 1 index value it will return. Negative indexing in NumPy allows you to access elements from the end of an array instead of the beginning, while positive indexes start from 0 and move forward. Negative indexes start from 1 and move backward. So 1 refers to the last element, 2 refers to the second last element, and 3 refers to the third last element, and so on. This works not only in 1D arrays, but also in 2D and 3D arrays. It gives 8 as the result as 8 third last from end. Slicing in NumPy is one of the most powerful ways to extract specific portions of an array without copying all the data. It lets us pick ranges of elements by specifying a start, stop, and step value. In this case, it pick first row on index value, which is 2, and second case, it will fetch first row 2 index value, which is 6. In a one-dimensional array, slicing works just like cutting a portion of a list. Array 1 is to 7 means picks elements from index 1 up to index 6. Now let's try for two-dimensional array 0th index. Row 1, 3, it will fetch from 1 up to 2 index.
When we write R0123, we are slicing inside a 3D array. A 3D array is organized as layers, rows, and columns. Here, the three parts mean 0, select the first layer, 1. From that layer, select the second row, 2, 3, and from that row, take a slice of the columns, starting at index 2 and ending before index 3. Since 2, 3 is a slice, not a single index, it returns the element at column 2 as a small array, not a single value. So R0, 1, 2, 3 means from layer 0, row 1, take the columns from index 2 up to, but not including, index 3. In simple terms, it extracts a column slice from that row, resulting in a small one-element array. When we use negative indexing in NumPy, we are counting positions from the end of the array instead of the beginning. While positive indexes start from 0 and move forward, negative indexes start from -1 and move backward. So when you write ARR -1, NumPy goes to fetch all the elements except.
That's all for today. I hope you learned something new. Make sure to hit the like button and subscribe for more easy explanations. Catch you in the next one.